This is chapter 2, the second lecture. We're beginning with geometric isomers, and this will wrap up our discussion of isomers in chapter 2. An example of geometric isomers would be 1,2-dimethylcyclohexane. So in the structures on this slide, you can see that the methyl groups can be equatorial to each other, and if it ring flips, they will be axial. And if you have one axial and one equatorial, when it flips, you still have the same. It results in one axial and one equatorial. So moving on to a summary of isomers. You can have the same bonding, which would be stereoisomers, and they can be interconvertible by a single bond rotation. Those are conformational or rotamers, conformational isomers or rotamers. If they are not interconvertible by a single bond formation, they are configurational isomers. Now, if they are different in the bonding pattern, they are structural or constitutional isomers. Let's start talking about chemical reactions of alkanes. In general, they're rather stable. They don't react with acids or bases or oxidizing or reducing agents. They do react with molecular oxygen and halogen. We're going to omit the oxidation of alkanes and skip ahead to the halogenation of alkanes, which is a free radical process, and we use light or heat to break a halide-halide bond, forming two halide free radicals. So the halogenation of alkanes is a substitution reaction where a halide, typically a bromine or a chlorine, is substituted for a hydrogen atom in the alkane. And this slide shows the general reaction sequence or formula for the reaction. We've got an alkane, which is indicated by the R group, showing the hydrogen on there. That's going to react with our chlorine or bromine, which is Cl2 or Br2. In the presence of heat or light, we'll form an alkyl halide, and HX, which would be HCl or HBr. So how does this occur? There are three steps involved. The first one is initiation. This is where a free radical is formed. You see the Cl2 molecule and a arrow. This is very important throughout the course. The arrows describe the movement of electrons in what's called a reaction mechanism. So the Cl2 will take one electron, will go to each chlorine atom to form chlorine radicals, two chlorine radicals. The next step in the sequence is called propagation. The chlorine radical can then react with our alkane and cleave or split off the hydrogen. And in this case, one electron that forms the RH bond will combine with the chlorine radical, okay, to form the HCl, leaving an R radical or an alkyl radical. The second step in the propagation is the alkyl radical reacting now with another Cl2. That again is going to split homolytically, which is one electron to each chlorine, to form our alkyl chloride and another chlorine radical. And that chlorine radical now can continue to produce other radicals. The final step of this is termination. So how can the reaction terminate? You can have two chlorine radicals combined to form Cl2. You can have two alkyl radicals combined to form the middle equation, which is RR. Or you can have an alkyl radical and a chloride radical forming the alkyl chloride. So a single alkane molecule can undergo several substitution steps, depending on the concentration of the halide radical. So here we have chloromethane with Cl2. That can produce dichloromethane, where we've installed two chlorine atoms on that molecule. Notice the boiling point. This is interesting. So we've added two chlorines, and we've gone up to a boiling point of 40. This now can react with another chlorine molecule to form trichloromethane, also called chloroform. Now our boiling point goes up from 40 to 61.7. A further chlorination of this molecule will form carbon tetrachloride. Now the boiling point goes up to 76.5. So far we've talked about chlorination or bromination of alkanes, but we've used a very simple model. We've used methane or methyl chloride proceeding to carbon tetrachloride. Well, what if the chain is branched or longer? Are the radicals all the same? And the answer is absolutely not. The more carbon substituents you have on the radical, the greater the stability. So this slide, which means that the radical is easier to form since the radical is more stable. So a tertiary radical is easier to form than a secondary and then a primary. So now, what about the difference between bromine and chlorine radicals? The bromines are less reactive than the chlorine radicals, so they're more selective in the reactions it prefers. And it prefers the weaker CH bonds, which leads you to think that the tertiary, right, which is a weaker CH bond, will react preferentially with bromine, and that's exactly what we see. It's about 1,600 times as reactive as chlorine. So just to summarize, if you want a tertiary halide, use bromine, right, since it's 1,600 times more likely than a primary and 20 times more likely than a secondary. So if you want a secondary, if no tertiary carbon is present, use bromine. And in the primary situation, use chlorine, but you will have a mixture of products. So that concludes Chapter 2. Again, I suggest you work through all of the homework, all of the assigned homework problems more than once to get a firm handle on the material. And if you have any questions, please contact your instructor.